All right, so in this video, I'm going to prove that L infinity is a complete metric space. So to start with, we're trying to show that this is complete, and so we need a Cauchy sequence. So the way that I'm going to write that is xrn, r greater than or equal to 1. So we're going to let this be a Cauchy sequence. What I mean by this is that for each choice of r, xrn is a sequence in L infinity. Right? So you can think of this that like x1n is really just a sequence of numbers x11, x12, x13, ... So that's its own sequence. And then similarly, x21, x22, and so on like that. So each one of these is a sequence of numbers, and you can kind of think of them as being in an array like this that goes down infinitely far. So what we want to do is we want to produce a candidate for a limit, because we have this sequence of sequences. We want to show that it has a limit in the sup norm. And we also want to show that that limit is in L infinity. So these are our two goals. So to show that it has a limit, first of all, we're going to fix n. And you can imagine that for a fixed n, there's kind of like a column. There's like an associated column. Like if n is 1, x11, x21, x31, ... is all the numbers in this column. And we know that like if we let epsilon be bigger than 0, there exists n such that, I guess I'll say like I and j. So if I and j are greater than or equal to big N, what this implies is that sup x I k minus xj k taken over all k is less than epsilon. And for our fixed n, we're kind of just looking at a specific case of this, right? So this says that for these two sequences, if you take the difference of their terms, the supremum over all of the terms is less than epsilon. But for a fixed n, you're just looking at kind of like one of the terms, right? So this implies that actually xin minus xjn is less than epsilon. Again, for any I and j that are at least as large as n. Okay, but we know that, again, if we fix the n, now we're just looking at a specific column. So this is really just saying that for the numbers in the nth column, they form a Cauchy sequence, right? So this is just saying that the numbers, again, n is the one that's fixed, right? So like the numbers x1n, x2n, ... form a Cauchy sequence. And this is how we're going to get our candidate for the limit. Right, because what does this imply? It implies that xrn, the limit of this, as r goes to infinity, is a real number. So this is basically saying, again, if you go down one of these specific columns, that those numbers kind of converge to a number. So you can denote that by, like, for this column, it's like S1, S2, S3, and so on. So xrn converges to a sequence, which we can call Sn. And this is what we want, because we want now to show that, because this is for a fixed n. Sorry, yeah, this shouldn't actually say this. because this is just a number. Yeah, so for a fixed n, xnr converges to Sn. But now we want to show that the convergence happens in the sup norm. So we want to show that if I take the supremum over all n, that this difference can be made less than epsilon for n sufficiently large, right? Like for n greater than or equal to some big N. Because we just showed that for each column the numbers converge to something, but now we want to show that our sequence of sequences converges to Sn, which is a different statement, right? However, what we know again is that because this is Cauchy, we can definitely make xin minus xjn less than epsilon for a specific n, and for I and j, again, sufficiently large. And so what you can kind of do with this is you can just take the limit as j goes to infinity, right? So the limit as j goes to infinity of this expression, again, we actually just showed that if this number up here goes to infinity, then the numbers in the column converge to Sn. And so that tells us that xni minus Sn is less than or equal to epsilon. So this does show that if I is large enough, then this is true for any specific choice of n. And so it follows that for all I large enough, again, like for all I greater than or equal to big N, that the supremum over n of this is less than or equal to epsilon. And this does give you what you want now, because this shows that, again, xr n converges to Sn. And now we've showed that it converges in the supremum norm, as opposed to just saying that in each individual column the numbers converge to the entries of Sn. Great, so this is what we want, and so the only remaining thing to actually show is that Sn as a sequence belongs to L infinity. And to do that, we can use a general fact about metric spaces, which is that Cauchy sequences are bounded. So we know that this is bounded. And specifically, it's bounded in the supremum norm, right? But since, Sn is the limit in the supremum norm of a bounded sequence, that does mean that Sn is bounded. If you wanted to make this a little bit more explicit, you could say that, for any possible choice of R, there's kind of a uniform bound on the size of xrn. So, you know that this is true for some non-negative real number m. And, in particular, this means that, again, for any choice of R and for any choice of n, this is true, because if this inequality holds for the supremum, this inequality definitely holds for individual numbers in the sequence, right? But you also know that if you pick your R large enough, then xnr minus Sn, that this can be made less than epsilon, or equivalently that this is true. And again, this is just like if R is large enough and for any choice of n, we have that this is true. But, by what we just said, this is greater than or equal to m minus epsilon, right? And then this one over here is less than or equal to m plus epsilon. And because the Sn is kind of trapped in the middle, right? It shows that m minus epsilon is less than or equal to sorry, this up here should actually be negative m minus epsilon. Sorry about that. So this is negative m. And so we know that this is true. And so, in fact, that just means that the absolute value of Sn is less than m plus epsilon. And because this is true for any epsilon that you care to choose, and because it's true for each n, right, it follows that the supremum norm of Sn is bounded by m plus epsilon. So that is a more explicit way to see why it's in L infinity. But yeah, that's it. We basically showed that every Cauchy sequence in L infinity converges to something in L infinity. So that's it. Thanks for watching.